Hi, my name is Ian Keller. I'm making this video for the Robbinsville High School Computer Science Honors Society. In this video, I'll be discussing basic algorithms and dynamic connectivity. In this video, I'll be discussing the procedure to develop a useful algorithm and then applying it through the dynamic connectivity problem. So first of all, what is an algorithm? Algorithms are simply sets of code that are written to produce a specific output or solve a problem. But making an algorithm is not just as simple as solving the problems. Making a good algorithm requires it to be fast, even if you're working with thousands or even millions of inputs. And again, efficient with memory, even if you're, again, working with thousands or millions of inputs. It should be error and bug-free, and it should be reusable, so that way you can use it multiple times in your project, or if you're going to publish it in a library, making it easy to implement in other people's projects. Now, there are a couple of basic steps to design a useful algorithm. The first thing you want to do is model the problem, so that way you know what you're trying to solve, and then you want to find an algorithm that can solve it. There are many kinds of algorithms out there, so you'll want to experiment and code up an implementation that works best for your problem. Then, you need to check for your speed and memory usage to ensure that it's running smoothly, quickly, and efficiently. And if it's not, figure out why. Then, once you've figured out your issue, find a way to address it, and then repeat until you have reached a satisfactory algorithm to use. Alright, so now we're going to take the procedure we just described and apply it to this, the dynamic connectivity problem. The dynamic connectivity problem simply is, if you're given a set of n objects, you may connect two components and check if there is a path between two components. The main algorithm we use for the dynamic connectivity problem is called union find. It contains two main methods: the union method, which connects two components together, and the connected method, which checks if there's a path between two components. Here's an example of dynamic connectivity and the way union find addresses this problem. So here we have a set of 10 integer objects, and we're just going to call it union and connected to show how it works. So we call union 4, 3, now there's a connection between 3 and 4. Again, call union 3 and 8, now there's a connection there. 6, 5, 9, 4, 1, 2, 1, there's all connections between them. Now we're going to call connected. First thing we're going to call is connected 0 and 7. It's going to return false because there's no path between 0 and 7 that the computer can use to, connect them. But then if we call, say, connected 8 and 9, even though there's not, 8 and 9 aren't connected, there still is a path available that will connect 8 and 9, so it returns true. Alright, so the first algorithm that we're going to discuss is the quick find algorithm. So the quick find is an eager approach algorithm, which means that it executes immediately and returns a result immediately. The data structure supporting this algorithm will be an integer array named ID of size n, where, again, n is the number of objects in the problem. Components are named by their index. As you can see, the index of the array corresponds to the name of the object on the right. And two components are connected if and only if they have the same ID. So, for example, if you compare the array on the left to the problem on the right, 1 and 2 share the same ID of 1, so they are connected. And same thing if you look at 3, 4, 8, and 9, they all have ID 8, which means all 4 of them are connected. So for the union command, what we're going to do is change all entries of ID P, which is of ID argument P, to the ID of argument Q. And then for the find command, we check if P and Q have the same ID. Alright, so now we're going to analyze our quick find algorithm, but before we do that, I just want to quickly bring up our procedure. So far, we've modeled the problem, we've shown our little grid, and we found our union find algorithm to solve it, and we've coded up the implementation of quick find. The next thing we need to do is check for speed and memory usage, and this is where the problems start. The big problem with quick find is that the union command is just too slow. It takes n squared array accesses to process a sequence of n union commands on n objects. And the problem with that is that quadratic algorithms do not scale with technology and thus must be avoided. What I mean by this is if you have a million inputs, if you have n squared array accesses, it doesn't matter if you have a supercomputer, it's still going to take an extremely long amount of time. That's what it means by doesn't scale with technology. So that's why we need to avoid quadratic algorithms, because they are just too slow, no matter what kind of hardware you're running. So instead, we have a second algorithm, which is called quick union. The quick union algorithm is a lazy approach, which means it will defer computation until it is absolutely necessary to execute, and then return the output only after that. Once again, our data structure is integer array ID of size n, but this time it's following a tree format where ID of I is the parent of I, and the root, or the top of the tree, or the bottom of the tree, is ID of ID of ID of so on, all the way until you get to a point where the ID of I equals I. So for our union command, we set the ID of P's root to the ID of Q's root, and for find we check if P and Q have the same root. So as you can see on the right, if we're looking at checking if 3 is connected to 9, we go to index 3, we see it's 4, we go to index 4, we see it's 9, and we go to 9, which equals 9, so we know that P and Q are connected because they have the same root, because 9 is the root. So same thing applies for 3. If we wanted to check 3 and 2, we go to 3, we go down the tree, its root is 9, we go to 2, its root is 9, so they are connected. So now let's analyze quick union. The problem with this one is that the trees can get too tall, which increases the time for the find command to execute, because we have to go all the way up the tree twice when we're trying to do the find. So, which makes it too slow when the trees get too tall. Overall, it's still faster than quick find, but it's still too slow for our liking. But it is an improvement, and now we can take our quick union function and improve it further. So I'm just going to talk about these quickly, but the first improvement we can make is weighting, where we modify quick union to avoid tall trees. So we're going to keep track of our tree sizes and balance the trees by linking the root of the smaller tree to the root of the taller tree. That way it always puts the larger trees lower, which reduces the overall height of all the trees. And then the second improvement is we can make is path compression, which just after calculating the root of P, we set the ID of each examined node to point to that root, which helps to keep the paths as short as possible, so that way the find command takes much less time to execute. Both of these improvements, combined with the quick union algorithm, causes it to become close to linear speed, which is what we want. At this point in our process, we've reached a point where the algorithm is very efficient now, so we can be satisfied with the result of our algorithm. So there you go. That was a demonstration of the way in which we develop algorithms, as well as an example implementation of an algorithm for the dynamic connectivity problem. Thank you for watching.